at an FSU graduation. He has an amazing career contributing in a broad range of scientific literature, from permafrost decomposition and methane gas release to the atmosphere in the Arctic, to the fates of the deepwater horizon oil and gas, and many more topics. Jeff is the John Widmer Winchester Professor of Oceanography. And as an aside, there is a wonderful obituary today in the Tallahassee paper about the incredible contributions Professor Winchester made to undergraduate and graduate education and research. So you can see there just how highly Professor Chanton is appreciated in the department to be named Professor Winchester, Professor of Oceanography. Professor Chanton is also the 2017-2018 Robert O. Lawton Distinguished Professor, the highest honor the university bestows on its faculty. In 2005, Professor Chanton received an award as the Florida Wildlife Federation Conservation Communicator of the Year. So we will take a great advantage of those communication skills today. He has given multiple presentations to elected officials, their delegates, and the public on the science of climate change, sea level change, and the oil spill. Please join me in welcoming Jeff to our program.
Thank you, Kim. So I'm going to go ahead and share the screen. We'll just start right into this. This is going to have a little PowerPoint there. And can everyone see that now?
Yes.
And is my volume good?
Yes.
Yeah.
Okay. Well, what I'm going to talk to you about is the history of Earth's climate from the Cretaceous to the present. Okay. Okay. So a lot of climate skeptics are always saying, and you still hear them say this, the Earth's climate is always changing, so we can't do anything about that. It's always changing. But just because it always changes doesn't mean that it changes capriciously, or that we can't predict it, or that we can't affect it. Climate is not as random as weather. And the Earth's climate, as we're going to see, is sensitive to very small changes, and humans are a significant enough force to affect climate change. I see I spelled effect wrong there. I should have used a effect. Okay, so what we're going to do is we're going to talk about, well, from the Cretaceous was about 100 million years ago. We're going to start 60 million years ago. But the Cretaceous was a hothouse world, and that's when the dinosaurs were roaming the Earth. And you can see that there's a dinosaur here, and there's a lot of palm trees. And so the whole Cretaceous was a very, very warm period. And then we're going to go into the Pleistocene, and the Pleistocene is the Ice Age. And so here we see a woolly mammoth. This is from the La Brea tar pits, and it's not a real woolly mammoth. It's just a replica of one stuck in the tar. So we're going to go from the dinosaurs on a 1,000,000-year time scale, 100 million years ago, to a 1,000-year time scale, 100,000 years ago in the Pleistocene, and on up to the present. Okay, so think about time scales as millions of years, thousands of years, and then we'll get into centuries. Okay, what we're going to be talking about is reservoir transfer. We're going to talk about the transfer of carbon between the lithosphere, that's the Earth's crust, the hydrosphere, that's the ocean, and the atmosphere. And of these three reservoirs, the atmosphere is the least dense, it has the less mass, and it's the easiest to change. But interestingly enough, of these three reservoirs, the only one that you can discharge waste into for free is the atmosphere. Okay, like if you think about your solid waste, your garbage, you roll your bin out to the curb and they take it and they bury it in the lithosphere. And you pay for that. And that waste is managed in a responsible way. And then your sewage goes out to the hydrosphere, right? You flush your commode into the water, and it goes out and it gets treated and it gets discharged and it goes into the hydrosphere. And you treat that responsibly for the most part. We do a pretty good job here in Tallahassee. We do an excellent job of that. And so those waste streams are treated and taken care of. Atmosphere, you can discharge your waste into the atmosphere for free, no charge. And that is the tailpipe on the back of your car. That's the smokestacks at the power plants. And so the reservoir that's the most sensitive to waste input, we get to dump into for free. And that has consequences. Okay, so here is, whoops, I skipped one. I gave away the answer. This is a quiz for the undergraduates, and I give them this question. And it says, the Earth's lower atmosphere, the troposphere, is heated from the radiation of what celestial body? Okay, so everybody in the chat, I want you to answer A, B, or C, and we'll look back and see what you put. Okay, so answer A, the Earth's atmosphere is heated from the radiation of the sun. The Earth's atmosphere is heated from the radiation of the moon, or the Earth's atmosphere is heated from the radiation of the Earth. Okay, so everybody's answered that question. And the answer is the Earth's atmosphere is heated from the radiation of the Earth itself. Who knew? Okay, very odd. Okay, and the way this works is the greenhouse effect, right? And I'm just going to explain this briefly. I'm going to explain it. I'm a mansplain it. So there's the sun, and the sun emits radiation in the visible wavelengths. And that's because it's really hot. So this is a thing called black body radiation, and the hotter something is, the shorter the wavelength that it radiates at. So the sun is very hot, it radiates shortwave radiation in the visible and UV bands. And that all comes into the Earth, hits the Earth. And the Earth's atmosphere is transparent to this visible UV radiation for the most part, because it comes right through, especially the visible. And a portion of that radiation is absorbed by the surface of the Earth, and it's shifted to longer wave radiation. I like to call it a redshift, but I think that confuses people. It's shifted to long wave, and it's re-emitted as infrared or heat. And the Earth's atmosphere is translucent or opaque to that heat. And what makes it opaque to the heat is the greenhouse gases, water vapor, CO2, methane, and nitrous oxide. And so by increasing the concentration of these things in the atmosphere, you can affect the trapping of heat, infrared radiation on the surface of the Earth. And it's just like a car parked in the mall. You go into the mall, you roll your windows up, you lock your car, and the sun is beaming its visible radiation through the windshield. And the windshield is completely transparent to that visible radiation. And that visible radiation hits the car seats and stuff like that inside the car, and it's redshifted to long wave radiation, and it becomes infrared. Part of it's reflected, right? Because you can see the car, and you can see inside the car. That's all reflected light. But part of it's redshifted and long wave radiation, that becomes infrared, and that is heat, and then that gets trapped inside the car because your windshield, like the Earth's atmosphere, is opaque to infrared or translucent to infrared. It doesn't go through the windshield, so the car heats up, and that's how the Earth's atmosphere works too. All right, now to the Cretaceous. The Cretaceous, everybody okay so far? We okay?
Yes.
Okay, all right. Cretaceous ended about 65 million years ago. And the Cretaceous was a really, really warm period for a number of reasons. And the thing about the Cretaceous was there was no ice on the Earth anywhere. Okay, the people had to drink their gin and tonics warm. Okay, there was no ice cubes. You could not get an ice cube. And because there was no ice on the surface of the Earth, all the ice that's stored on land today was in the ocean. And so the sea level was a lot higher than it is today. And here you can see the ocean. Can you see my cursor here, my mouse? The ocean ran up all through the western states. You could sail a boat if there were humans there. A human could have gone all the way up to the Arctic, and probably the dolphins did that. They'd swim right up to the Arctic, and they go this way. So there was a lot higher sea level. And Florida was formed at this time. It was a epicontinental sea, a shallow sea, like the Bahamas are today. And associated with that warmer world, the CO2 concentration was about 1,000 to 1,500 parts per million. That's microliters per liter for your chemists in the audience. Okay, we use ppmv for that. But today, the atmosphere is 410 parts per million of CO2. The pre-industrial atmosphere, before the Industrial Revolution in 1800, it was 280 parts per million. And at the height of the glacial period, which we call the Pleistocene, the CO2 concentration was 180 parts per million. And so associated with that warmer temperature on Earth, we had a CO2 concentration 3 or 4 times what it is today, and 5 times what it was in the pre-industrial times. And there's a lot of reasons for this: a better heat distribution system, but there was also higher CO2, and that higher CO2 we can explain because there was a lot of seafloor spreading and volcanism. So it was a hothouse world, all the palm trees. We saw this picture already. Here's an artist's rendition of the Cretaceous period. And one of the things that you notice in this, as highlighted by this yellow arrow, is volcano, okay? And so the high volcanism of the Cretaceous period emitted a lot of CO2 and made the CO2 concentration high, and that's a lot to do with why it was so warm and no ice caps and high seas. All right, so now we're going to have to really pay attention, all right? So we're going to talk about how there was this transition from this hothouse world, which ended about 60 million years ago. It peaked at 50 million years ago in a period called the Eocene. And ever since the Eocene, so on this graph, look at this graph first. We have time on the x-axis. And there's 2 graphs here. This is time 0. This is the present. And this is the Cretaceous. So a lot of these graphs go backwards in time. Time marches forward, right? We think of things going from right to left. So time is marching forward from the Cretaceous to the present. And this is the temperature of the deep ocean. And we know this, I'll tell you how we know this in a second. But here the temperature peaked about 50 million years ago. And then the temperature went down, 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 resulting in the ice age of the Pleistocene period about 2 million years ago. So we have falling temperatures. And this is when the ice on Earth began to develop. The Antarctic ice sheets formed first about 35 million years ago. And the North Hemisphere ice sheets, the Arctic, formed late in time, 4 or 5 million years ago. So we see the cooling Earth. And what's happening here is, let's look at this other graph first. Here we have the CO2 concentration. The best estimate of it is the solid line. The uncertainty, of which there is considerable uncertainty, is the yellow shaded area. But what you see here is the CO2 concentration was perhaps around 1,200 parts per million in the Cretaceous period, the dinosaur period. It peaked about 50 million years ago in the Eocene, and since then it's been falling, and it got very, very low, 180 parts per million in the Pleistocene glacial period, okay? And what this is due to is this transfer of carbon between the lithosphere and the atmosphere. So in the Eocene and the Cretaceous, when the CO2 is so high, there was a lot of volcanism, and volcanism was taking carbon from the lithosphere, from the solid Earth, and putting it into the atmosphere. And then we have this break in the volcanism, and the CO2 goes down. And I'm going to tell you what that's due to, but it is due to the transfer of the CO2 from the atmosphere back to the lithosphere. So this exchange between the atmosphere and the lithosphere controls the carbon dioxide temperature and the climate of Earth on a 1,000,000-year time scale. Okay, it takes 1,000,000 years for these changes to occur, and that's the time scale we're on right now, right? Because this graph has 0 down here and 60 here, and it's time before present, BP. That doesn't mean British Petroleum, it means BP, 1,000,000 years before present. Okay, everybody with me? More or less? Hope so. So how do we know this stuff, right? What are our paleo indicators, paleoproxies, we call them in the business. Well, we know the global temperature of the deep ocean from these little creatures that live in the ocean called forams, and they're little animals, and they are single-celled, and they have a calcium carbonate shell, and they record the oxygen isotope composition of the seawater, and that's related to ice volume and temperature. Okay, and that's another whole class to have to get that, but this is how we know that. And it's amazing the progress that we've made in the last 3 generations on learning this stuff. Science and scientists are quite remarkable people. And we know the CO2 concentration. This is an alkanone, and these are long chain ketones, and they're buried in the sediments. And they are very stable. And their C13 isotopic composition is related to the CO2 concentration. And so basically, it's stable isotopes. There's always in nature a bulk one, like carbon-12, and then there's a trace one, like carbon-13. There's a bulk oxygen, oxygen-16, and there's a trace one, oxygen-18. And we use these differences to learn about the history of the Earth. And that's all I have time to say about that right now. Oh, and the other thing is that these are, we go for these records, we find these records in sites of deposition where things accumulate. And so we have these deep sea sediments are building up every year, more sediment, more mud, more mud, more mud. And so time is death. And so if you look at the surface of the sediment core, say in the deep sea, and you go down that sediment core, that's a temporal record, a chronology. And so we get our chronologies that go back millions of years from deep sea sediments. I wish we could do questions and I could look in your eyes and see how you're taking this, but we're just going to have to go on. That's the Zoom world that we live in. It's a lack of human interaction. So, lacking human interaction, I will see. So, where does this volcanism come from? Okay, it's not like Mount St. Helens so much, but if you remember, I don't know, do you know plate tectonics? Do you know about seafloor spreading? Okay, because at the seafloor spreading, you have the mid-ocean ridge, which creates crust, and these things that we call seafloor trenches, we recycle the crust. And at the seafloor trench, where 2 plates collide, one plate, here is an oceanic plate, is thrust under the continental plate. So what we're going to be looking at is India and Asia. Okay, and here, this oceanic plate here in gray is being subducted under this continental plate of Asia. And as it does that, it melts, and there's all this calcium carbonate that's stored in the sediments on the surface of that plate. And all that calcium carbonate, when you heat up carbonate, it turns back into CO2 at 550 degrees C. And so all that carbonate comes up. All those little shells, those foreign shells, here they are playing another role. They turn into CO2 and they come out that volcano. So the rate of volcanism is proportional to the rate of seafloor spreading. And in the Cretaceous, seafloor spreading was on steroids. Okay, we don't really know why, but it was. So here is what controls the CO2 concentration on the Earth on a million-year timescale. I'm sorry, but this is reversed now. Here the plate is going down this way. I couldn't find one, it went the other way. You know, when you're stealing people's figures, you have to take the best you can. But here is that plate, okay? And there's calcium carbonate that's coming from these shells. And they're coming down onto the plate. They're going down the seafloor. And they get heated up. And you have this thing called metamorphic decarbonation. And calcium carbonate from those shells reacts with silicon dioxide to form calcium silicate, that's rock, and CO2. Right there's the CO2. That CO2 comes out the top of the volcano and goes into the air. So that's, here we have transfer from the lithosphere, right? Because that carbonate's on this plate and it's being subducted, heated up, and turned into CO2. So lithosphere, from the lithosphere to the atmosphere. Okay, and then when you form a mountain, there's a process called weathering. And CO2 is a highly soluble gas, and it reacts with water to form a thing called carbonic acid. And that carbonic acid attacks the rocks and dissolves and forms dissolved carbonate, which goes back to the ocean and forms more shells. Okay? So the balance between these two processes controls the surface CO2 concentration in the atmosphere. Now, interestingly, about 80 million years ago, the continent of India was not attached to Asia. It was located down on Antarctica. And so India, 80 million years ago, it says right here in the text, was located 6,400 kilometers south of the Asian continent. And India was on a plate by itself, and that plate was rapidly moving across the seafloor at a rate of 9 meters per century. Okay, that's almost 30 feet a century. That's like 9 centimeters, this much, every year. Okay, well, I can't do it. Anyway, it's a good bit of a foot every year. India moving across the seafloor. Okay, and then it rammed into Asia about 52 million years ago. And when it did that, that began the uplift of the Himalayas, and that changed everything. So here we have an artist's rendition of this process. Here we have Asia, okay? And here we have India, on this side, India. And India is on its own plate, and Asia is on its own plate. And India is rapidly galloping across the seafloor, 9 meters per century. And that plate, India is a continent, right? But it has a leading edge of oceanic plate. And that leading edge of oceanic plate is being subducted under Asia and causing volcanism and CO2 emissions. And here we have all the sea surface, and those forams are forming in the surface ocean, and they're sinking down here, and they're getting onto the continental plate, or the oceanic plate, excuse me, and they're being subducted, and they're melting, and CO2 is being emitted. Okay, and this transfers carbon from the lithosphere to the atmosphere.
Hey, Jeff, really quick.
Yeah.
We're getting some feedback on our Zoom chat saying that your audio is breaking up a little.
Dear.
I'm hearing you, but it's difficult to hear you. So I mean, I'm following along. I imagine some people are as well. But so maybe just check your microphone.
Yeah, Wallace, it sounds like Jeff is more clear when he's closer to the computer for some reason.
How's that right there? Like that?
That's perfect, man. That is really good.
Okay.
That's very good.
All right. I'll just hunker down here next to the computer. All right. So should I repeat that? Like, here's India in this corner. Here's Asia. The oceanic crust is going along, being subducted. The forams form in the surface ocean. They're made of calcium carbonate. They sink. They're deposited on this lithospheric plate. They're subducted, and they're heated up, and they come out as CO2. And so during this process, in the Cretaceous, CO2 is being added to the atmosphere at a very substantial amount. Okay? And then here we have India is getting closer to Asia, but the process still continues, right? And then the next thing that happens is India and Asia collide. And when this happens, you no longer have seafloor subduction. What happens now is that you have a process called orogeny, or mountain building. So that subduction stops, and the CO2 that was being released is no longer released. But you're building up this gigantic mountain range, the Himalayas, the Tibetan Plateau. And when you do that, you shift from volcanism emitting CO2 to the weathering process consuming CO2. How's my sound now? Does the sound okay?
It's about the same.
Not any better?
Huh? My theory is when you're moving your mouse, something is happening, because now it's perfect.
Oh, down here it's perfect?
Yeah. Now or what are you, kissing the screen at this point?
Almost. I'm right on top of it. Okay.
Sorry.
That's okay. But that's better down here. If it starts to break up, just say something to me and I'll move closer. Okay?
Yes, sir. Yes, sir.
All right. Stay with me. Just let me know. Okay, so we build up this big mountain range and we start to have more weathering. And there it is. It's a gigantic mountain range built up by India ramming into Asia. And so weathering, this is the process of weathering. CO2 plus water forms carbonic acid. And then that carbonic acid attacks the rocks and it forms bicarbonate and silicic acid, and that runs down into the ocean where it forms calcium carbonate shells. Okay, so now we're transferring material from the atmosphere back to the lithosphere because of the Himalayas. And that forms these shells, and these are deposited on the sea floor. And that's our lithospheric deposition. Sound okay?
It
No?
was okay until you went to this slide.
This slide here.
It started crackling again when you went to that slide.
Okay.
Now you sound all right, though.
I have another microphone I could use. Should I switch to another microphone, you think?
Might be worth a try.
Yeah, let's see if this works.
There won't be a test after this, will there be?
Okay.
My wife was texting me the answers.
Can you hear me now? Is that good? Okay,
Sounds-
this is
Sounds good.
using the
This is
iPhone.
great.
Okay, iPhone microphone. All right, so I hope anybody has gotten something out of this so far. So here is that temperature record. And it's amazing that the temperature had this maximum at 50 million years. And that is roughly coincident with when India rammed into Asia. And we went from the process of seafloor subduction to a process of weathering of the Himalayas. And when that happened, the CO2 concentration went down, okay? And that's because here we're transferring material from the lithospheric plate to the atmosphere, so CO2 is high. Then we start weathering process because we're not doing any more seafloor subduction. We are now weathering the Himalayas. And that changed the whole world. And the CO2 goes down, 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 down because of weathering. And then the first ice sheets start to form about 30 million years ago in Antarctica, okay? And CO2 continues to fall. And when you form these ice sheets, you have another process that is going to cool the Earth, okay? So as the CO2 is going down here, the Earth's getting cooler, right? CO2 is decreasing, temperature is decreasing. Now we have a second process that's going to decrease the temperature. And that's the increasing ice cover, because ice cover reflects sunlight. If you've ever been snow skiing, you know that if you forget your sunglasses on a bright sunny day, it hurts your eyes. There's so much reflection. And that's called the Earth's albedo. Not to be confused with libido, okay, albedo. And so you have more reflection, and that cools the Earth because instead of absorbing the sunlight, the visible radiation, it's now reflecting it, okay? And as that ice sheet grows more and more, you have more and more reflection. And so the temperature falls more and more and more. And it really starts to fall when you form the Arctic ice sheets. It really falls in a lot. And so then we get in, and so these two processes are causing these positive feedbacks, which I don't really have the time to explain all of it, but they're both feeding on each other. And so the colder temperature brings down the CO2 falling brings down the temperature, the ice sheets form, it gets cooler, and so the Earth is in this positive feedback mode. And the cooler it gets, the more ice sheets you get, cooler it gets, the CO2 goes down. Both these processes are self-feeding. They're called positive feedbacks. And so then we get these ice sheets accumulating. And this is another place then that we can get a chronology. Our previous chronology came from the deep sea. Now we can get a chronology from the Arctic ice sheets. So scientists go to the Arctic and to the Antarctic, and we take these long cores, and you get an ice core like this, and the ice core has a temporal record of temperature from the oxygen isotopes of the water, like the thorium, but it also stores little bubbles of the atmosphere. And so the ice sheet is like this sample collection device that's been left for humankind. And the ice sheets have been collecting samples of the atmosphere since the time they've been formed. And we can go and get these cores and we slice up. And the deeper you go in the core, the older the time is. And all this atmosphere is stored, okay, because here's the snowpack. And the snowpack air diffuses and exchanges freely through it. But then as that ice sheet, as that snowpack turns to ice sheet, it traps bubbles of the atmosphere within it and seals them up. And so you have samples of the atmosphere stored over time in these cores. Okay, it's really quite remarkable. And what we find is that this Pleistocene period was digital. Climate at that time became digital. It had two forms: glacial form, where the ice sheets came all the way down to New Jersey, and interglacial form, like we're in the pre-industrial age today, okay, 1800. So ice sheets here in the Arctic Ocean and Greenland, that's the interglacial. The glacial period, the ice sheets came all the way down to New Jersey. And when you have all this ice stored on land, then the sea level is lower. And in fact, during the glacial period, the sea level was about 300 feet or 100 meters lower than it is today. Okay, I've only got about 10 more minutes here. I'm sorry, but I got a little distracted by the microphone issues. So this is a record in the Pleistocene. Now we're on this 100,000 year time scale. Remember I was talking about the million-year time scale and 100,000 year time scale. We go from 0 to 800,000 years. And we get the temperature is the red here. There's our present day temperature. And that's the present interglacial period that we're in. There's the last interglacial. There's another interglacial, interglacial. And they come about every 100,000 years. And then the black is the CO2, is the temperature. So this is the CO2 concentration here. The red is CO2, and the black is temperature. And you can see that these two coincide remarkably well. They're following each other, they're highly correlated. And the green is the methane concentration, another global warming greenhouse gas. Okay, so temperature was varying in concert with CO2. CO2 was at a maximum of 280 parts per million during the interglacial periods, the warm periods, and it was at 180 during the glacial periods when it was really cold. And then we have the Industrial Revolution, and there's CO2 concentration there, and the CO2 shoots up, it's at 400 now, and we see that there's always been this tight correlation between temperature and CO2, so we might expect the temperature to go up as well as the CO2 does, because temperature and CO2 have always followed each other remarkably well. They're highly correlated. And as I said, during the Pleistocene, sea level was lower. This is the coastline of Florida 18,000 years ago. And so sea level rises with temperature. Okay, so what's new? A biological force on par with the geological processes is transferring buried carbon from the lithosphere to the atmosphere on very rapid timescales. The coal and oil and gas that we have come from the lithosphere. And when burned, they add CO2 to the atmosphere. And that is the Anthropocenic burning of fossil fuel. So here we have our CO2 concentration going back 400,000 years ago. The interglacials are at 280. Over here is the scale, 280. In the glacial periods, it bottoms out at 180. And then we have the Holocene period. The glaciers melted about 18,000 years ago. The CO2 went up to 280. And then we have the Industrial Revolution. And humankind figures out that we can burn coal and produce energy, oil and produce energy. And so the CO2 goes up. And right now it's above 400. And at the rate we're going at with the CO2 concentration, CO2 emission rates, by the year 2100, it will be approaching 700 parts per million. And that's halfway back to the Cretaceous. So by the year 2100, in 80 years, we will be halfway back to the Cretaceous. And so you might expect that that's going to have some effect on temperature, okay? Because going back to this record, we see that 100 parts per million change in CO2 was correlated with a 8-degree shift in temperature. Okay, so we're taking CO2 from 280 all the way up to 700, and we might expect that there would be a temperature increase associated with that. That would be a reasonable hypothesis. Here we have more recent ice cores from the Arctic, and this is on a 1,000-year time scale. Here's the year 2000 here. We'll just look at the CO2. Here's the year 1000. CO2 is constant all through the Middle Ages. And then at about 1800, you see an exponential increase associated with burning of oil and coal. And of course, that allowed the human population to develop. Okay, as an oceanographer, I always say that the deep sea is a very barren, void place. Sometimes it occurs that a large resource like a whale will fall in, a whale fall, and then that allows a population of deep sea organisms to explode. And so for human beings, the whale fall is the finding of fossil fuel under our feet, and that has allowed our population to explode as well. Sea level, because that's what concerns us here in Florida, is controlled by two things: the ice volume and the temperature. Because when the ice melts, it flows into the sea. And when the temperature warms up, the ocean water expands and takes up more room. So both of these processes are causing sea level to rise. And I'm sure everybody's heard of Bruce Means. This is a picture he took when he was 14 in Anchorage. And there's this glacier here. He went back there when he was 66 in 2007. The glacier was gone. So all that glacial ice ran into the sea and caused sea level to rise. Associated with that rising sea level and melting glacial ice is a decrease in the Earth's albedo. So this now has a positive feedback to warm the Earth, as does the rising CO2. So if both these processes are acting out, instead of cooling the Earth, melting the glaciers and the rising CO2 concentration are increasing the Earth's temperature. And here we have Florida. Faced with these rising seas, we have a very flat coastline, and so a 1 foot rise in sea level results in tens of feet of shoreline retreat. Okay, so that's the main problem for us here in Florida. And on what features will the sea level rise be imposed? Barrier islands and river deltas. Both these features, these geologic features where we inhabit so much of the Earth, were formed in the late Holocene when rates of sea level slowed down. So here's the sea level curve for the Holocene, and here we have thousands of years ago before present, 0 to 20. Sea level on this axis in meters, from present day sea level to minus 120. Sea level when the glaciers melted, it rose very, very rapidly. Then about 6,000 to 8,000 years ago, we have what's called a sea level still stand, and it stopped rising. And that's when the barrier islands formed and all the deltas formed where all the people live. And if sea level rise picks up to a rapid rate, which it seems like it might well do, what is going to be the stability of these coastal features where everyone lives? So here's what's projected for sea level. Here's the sea level curve. These are based on tidal gauge records, and then later on satellites, that's orange. You can see that from 1700 to 1800, the beginning of the Industrial Revolution, that's the year down here, sea level in meters here. Sea level was very flat, wasn't rising. From 1800 to 1900, you can begin to see that it might be rising a little bit, but certainly from 1900 to the year 2000, the rate has increased more and more rapidly. And so these are some projections for the year 2100, anywhere from 0.4 meters to 1.2 meters. And these are conservative projections from the IPCC. So 50% of Florida's coastal areas are critical erosion zones. That's all the red areas here. The blue areas are not critical erosion zones. That's only because they're undeveloped. So all of these areas of Florida are eroding. These beaches are renourished by the pumping of sand from offshore at considerable expense to taxpayers. That's how we maintain our beaches, because they're eroding otherwise. This is a map of Louisiana. that they have on their highway signs. It's a false advertisement because Louisiana looked like that in 1839, 1870, 1993, and here we are now. The state of Louisiana is rapidly eroding and going into the sea. This is from 1960 in Spain. This is what it looked like. Here's that same place in year 2000. So coastal development is rampant. And we're developing a place that's highly vulnerable to sea level rise. This is our own coast of Florida along the Atlantic. And you can see there's very little space here between the ocean and the swimming pool. This is Tybee Island, Georgia, during the king tide. The mayor of Tybee Island has a job on land and can't get to it during certain periods because the road is flooded. This is a high tide. This is a nuclear power plant. Very little freeboard here. We're facing a rising sea. And this is a nuclear power plant in California. And notice the coastal erosion all around us, okay? The cliffs, the bluffs, the power plant protruding into the sea, kind of like the road to Cape San Blas out in Port St. Joe, maintained by this rock jetty. And this is the oil and gas infrastructure that we have in Louisiana, barely above sea level. And so we're going to be facing a lot of issues associated with climate change and the rising seas because of the rising CO2 and the melting of the glaciers, decreasing the Earth's albedo. And I'm sorry I went so fast, got a little rattled about the microphone issues, but I hope that some of this was worth listening to. And if anybody has any questions, or there are any questions in the chat, I'm happy to try to answer those. Sorry about the audio.
I have a question.
Okay.
So the setbacks that Florida started really aren't helping at all.
The coastal setbacks?
Yes.
Well, they're a little conservative, and so we might expect that they'll need to be rolled back. If you look at Alligator Point, you know, the road washed out again this summer.
Yes.
And so, yeah, the coastal setbacks were, you know, it's all changing so fast.
You have any suggestions on what we should be doing?
Well, you know, there's a lot of individual action that people can take and do take, like buying a Prius, using their clotheslines and stuff. But I really think that this is a societal problem, and that we have to act together as a society to take this problem, to address this problem. And the problem with acting as a society is that right now this is a time of individuality, and individual freedoms are paramount. And so getting people as a society to take this seriously is a really difficult thing. And so we need to act in concert and change rules and laws. And, you know, the current administration is doing just the opposite of all of this. They've, you know, all the fracking that goes on out in the West, the Obama administration had rules about capturing methane and tracking the release of methane from these operations, and the current administration has suspended all of those rules. And so we're going backwards at a pretty rapid clip right now.
We've got a couple of questions from the chat. The first one is from Father Dave, and I think it may have been answered, but it's, has the pandemic and relative decrease in emissions taught scientists anything? Well,
we see that CO2 concentrations do respond to human activity pretty rapidly. CO2 emissions did decrease significantly. And so that, you know, shows us that the problem is us. the number of airplanes, which use a lot of fossil fuels, the airplanes are flying less. So yeah, we've learned that we are responsible, but I kind of think we might have known that.
And then the next couple of questions are coming from David Wheeler. About how many scientists worldwide are studying climate change? What percentage are in general agreement with the information you've presented, and what percentage are opposed?
There's probably more agreement among scientists on this issue than any other thing that you could poll human beings about. Okay, if you have a group of people and you ask them, how many of you agree with this? If you ask scientists, the numbers are 96%. And I'm sure that if we were to poll this group of people on this call right now and ask them some question, we would probably have a higher diversity of opinion about almost anything. And so I think it's a pretty much unanimous consensus about this issue. I don't really understand the reluctance of our own government to not deal with it. It's just like so counterproductive. It's just makes no sense at all.
Professor, I have a question, first a comment. This has been an incredible presentation, but it seems to me that in your presentation, I came away with two thoughts. One,
Okay.
obviously, is the increased emission of CO2 into the atmosphere, starting with the industrial age and ramping up since then. The second is, and this is, I guess, my question. The second is that with the demise of the ice sheets, you're losing more and more reflectivity of heat. Why in the world then are we paving roads and building roofs that are dark in color that provide no reflection? I mean, it seems to me that as we're paving the entire world with white asphalt, that's a counterproductive in terms of reflection. I don't know whether it would make any difference. I know that there's two, or it seems to me there's two issues.
Yeah, well, you're certainly correct about that. The cities and all that asphalt does lead to this thing called the heat island effect. And so urban areas are considerably warmer than rural areas. And not only that, they hold on to that heat at night and they leave, so the nighttime temperatures are increasing in those heat islands and across the world as well. But that is, if we, higher reflectivity would be a good thing. However, the simplest solution would be to switch to some kind of power source that doesn't generate CO2.
Right.
Which we have the ability to do. It just costs a little bit more.
We've got one more question from the chat, and then I think also Dottie McPherson wanted to say something, but I'll ask the chat question first. This is coming from Pat Garner. Are the public dollars used in support of beach renourishment appropriate, or simply throwing good money after bad?
It's a temporary solution at best. It might last for a couple years, if that, but a lot of places they put the sand on and within 2 or 3 years it's gone. So it's a continual process to maintain those beaches.
Dottie, go ahead. I think you're unmuted now.
I have a question if Dottie's not going to come in yet. Yeah, just watching this presentation, it kind of takes the wind out of my sails. Feeling of lament and almost like despair for humanity. And our faith, our Christian faith, really calls us to be good stewards of the environment and to care for God's creation. And I just wonder, Dr. Chanton, have you seen any activities among people of faith who are kind of coalescing to take this message to the public, as opposed to what some politicians are doing in the other direction?
Yeah, I think a lot of churches are working towards, I know the Methodists in particular are very active in you know, Presbyterians and the Methodists are very active in spreading the word about this sort of stuff and trying to, you know, promote green energy and that sort of thing. So, you know, people are aware of it, and, you know, we have to help ourselves. I was at the Ace Hardware in Crawfordville the other day, and, you know, the pandemic has a lot to do with this too, I think. And there was a guy I was asking about where something is, and I had a mask on, and the guy that was working there didn't have a mask on, and he said, "It's really hard to hear you with that mask on." And I said, "Well, I'm wearing it for you." And he said, "Oh, I have all the protection I need." And I thought he was implying that the Lord would protect him, you know, and I should have said to him, "Yeah, the Lord sent me this mask to wear to protect you." You know, like, we have to use the tools that we have to take care of things. And I really think that, you know, the Trump administration's solution to the pandemic has been to ignore it and do nothing, and to put all of his eggs into this basket of getting a vaccine. And so rather than do something to limit the problem, he's looking for a technological solution to that problem. And I think that the climate thing is being treated in exactly the same way. It's ignoring the problem, and then just figuring, hopefully, if we keep our economy blazing hot, we're going to get a technological solution to this somehow. And, you know, I wonder, hope that works out for us. Because that's, you know, that's the eggs, that's the basket of eggs that we're looking at.
This is Father Dave. I want to encourage those that are part of this meeting today to check out a climate scientist who's also a person of faith. Her name is Catherine Hayhoe, and it's spelled Hayhoe. And Catherine is a really fascinating figure. She's part of the evangelical church, and she's really made it her mission, as she says, to go into, as she calls it, hostile environments, you know, environments where she knows that people are not going to agree with her, so that she can provide accurate information about where we are right now and how our faith can guide us in being a part of the solution rather than doing further damage. Another resource that I would encourage everyone to check out, for me, it's an organization that's doing the most good right now. It's called 350.org. 350.org. And it was founded by Bill McKibben and many others. And 350.org is taking a different tact right now. Rather than waiting for governments to do something, which, as we all know, can be pretty challenging sometimes, they are applying through direct action. They are applying a lot of pressure on financial firms, financial services who invest in fossil fuels. And interestingly enough, if you look at the portfolio of major investment companies, their portfolios are not highly reliant on fossil fuels. I mean, it's important, but it's not it's not their biggest investments. And so, you know, if you're asking ExxonMobil or or BP to stop doing what they're doing, that's their core business. They have no motivation to stop extracting energy from the earth. However, the financial services that fund them, if you put a lot of pressure on them, they are beginning to divest from fossil fuels because in reality, you know, everyone knows that those assets are not inexhaustible. So long story short, if you're looking for some of the more interesting things that are happening right now, whether there's people of faith or just people who are concerned about this, 350.org is a good resource.
True. And if I could answer Dottie McPherson's question here, she says, we've had 5 ice ages. Based on history, we'll have another. When looking at climate change, why aren't scientists looking at the relationship of the climate with the solar system? And that the solar system brings on heat and freezes. And that is the solar changes in the Earth's orbit. And the amount of sunlight that came into the Earth were what triggered those Pleistocene ice ages, the interglacials and glacials during the Pleistocene time. But at that time, the CO2 concentration was varying between 280 and 180. And so the Earth's climate at that time was very close. It was very easily influenced by these small changes in sunlight that were related to the orbital frequencies. But now we've left that period of the Pleistocene because our CO2 concentration is going up to 700, right? And so now we're in a new geological epoch that the scientists call the Anthropocene. And the climate sensitivity to the changes in the Earth's orbit is not going to be as great because the forcing now is driven by the emission of fossil fuels. Okay, and so humankind have just taken us into a whole new geological epoch. We are a geological force on this planet, changing the ratio of things from the lithosphere to the atmosphere.
I'm thinking the Earth needs a bunch of umbrellas.
When there's a volcano, the volcano puts all this dust and sulfate aerosols up into the atmosphere, and that temporarily lowers temperature. However, the lifetime of those particles in the atmosphere is much, much less than CO2 emissions. So you'd have to have continual blasts going up into the atmosphere and you don't know different countries would want to manage that in different ways, you know. Probably the Russians would have their idea about it and we would have a different idea.
Any last questions? We have 2 minutes left. Oh, we got a question. Kathy does.
You're muted.
Kathy.
Unmute, Kathy.
Here, I'll ask you.
Okay, now we can hear you.
Nope, Kathy, you're still muted. I'm so sorry. Oh, try it again. Try it again.
How about that?
Perfect.
Okay. Let's see. Let me gather my thoughts again.
Okay.
After all
I
that.
know this computer zooming thing could destroy your thoughts.
Anyway, this thing about 80 more years, between the point at which it gets so very obvious to everyone, and I mean, like, you know, 3 minutes to midnight kind of thing, that something has to be done. How quickly could something like this be turned around? Anybody's guess? Of course, we don't know what we'll have then in the way of technology or anything, but I'm just wondering if I mean, you know, America seems to be a country that just lets it get let a problem kind of run until they say, oh my gosh, and then throw everything on it. Like World War II.
The easiest solution is to limit methane emissions, you know, like natural gas. At all these fracking places, they leak a lot of gas out. And the Trump administration has eased the rules on monitoring those leaks and fixing them. The lifetime of methane in the atmosphere is about 7 to 10 years. So if we would reduce the methane emissions, we'd see a turnaround in the forcing of heat on the Earth's surface by the atmosphere in 10 years. So that's the place to start. And methane has a global warming potential that's 30 to 50 times that of CO2. And so limiting methane emissions is an easy, quick solution. But we're going the wrong way on this. We have to change I don't want to be political or anything, but we have to change our leadership. Or
would it help if all of us had a sheet of paper that had that information and were encouraged to write letters to people? I mean, I know this administration isn't listening all that well, but we may not have this one too much longer.
We can only hope. I'd be happy to provide, Claire, I could send something to you, or Tim, maybe you and me could work on it, Tim, and we could send it out to everyone, an information sheet.
Or just via email.
Yeah, sure.
That'd be awesome, and just kind of include my umbrella theory.
Okay. Well, aerosols is the way to go.
Thank you so much. This was an excellent
Thank you. Yes, thank you, Jeff. Thank
I'm
you for
sorry.
being with us.
Sorry, I got a little rushed there at the end. I got
No,
rattled
you're-
by the.
No.
I got rattled by the
good.
microphone.
Thanks so much, Jeff.
Yeah, sure.
And I'll be in touch.
Okay, good, good. Are you
Every-
you're gonna Tim? Will you be in Tallahassee in the fall?
I think so.
Good. Okay.
Yep.
All right. Thank you all very much for your attention.
Yeah, we thank you again, Jeff, for being with us, and Tim for the introduction. We will be back here next week, same time, same place on Zoom, and we'll celebrate the ministry of the bookstore. So a lot of good stuff next week. So please come back, and again, thank you for being with us today. Thank you, Dr. Chanton and Tim,
Sure.
for all your work.
Thank you for having me.
Everyone, have a good week.
Okay,
Thank
bye.
you.
Thank you very much.
Thank you.